In algebra, two expressions are called equivalent if they represent the exact same amount. This isn't just about sometimes being equal. They must have the same total value for every single number you could possibly substitute for the variable. For example, if you have the expression 2x and the expression x plus x, they are equivalent because they both mean the same thing, 2 times x. Our goal is to figure out when expressions that look different are actually the same. There are two main ways we can check if two expressions are equivalent. The first way, which is the most reliable, is to use the properties of operations, like the distributive property, to simplify both expressions until they can't be simplified any further. If they end up looking identical, they are equivalent. The second way is by substitution, where you plug in a test number for the variable to see if both expressions give the same result. Let's start with method 1, simplifying with properties. This method is the algebraic gold standard because it proves equivalence for all numbers, not just the one you test. Our goal is to use the commutative, associative, and distributive properties to break down each expression into its simplest possible form, known as its standard form. If the standard form of expression A is identical to the standard form of expression B, then we have proven they are equivalent. Here's a quick example using the commutative property. Take expression A, 5 plus y plus 3, and expression B, y plus 8. To simplify A, we use the commutative and associative properties to rearrange and group the constants, y plus parentheses 5 plus 3, close parentheses. That simplifies to y plus 8. Since y plus 8 is exactly the same as expression B, we know for sure they are equivalent. Next, let's use the distributive property to check. Expression C is 4 times the quantity x plus 1. Expression D is 4x plus 4. To simplify C, we distribute the 4. 4 times x is 4x, and 4 times 1 is 4. So expression C simplifies to 4x plus 4. Since that is identical to expression D, we conclude they are equivalent. You can see how the property itself is the tool that generates the equivalent expression. Method 2 is substitution. This is a great quick check, but you have to be careful. To do this, pick a small, easy-to-use number, like 2 or 3, and substitute it for the variable in both expressions. You then evaluate both expressions using the order of operations. If both expressions result in the same numerical answer, there's a good chance they're equivalent. So why can't we stop after just one test? Imagine you had x plus 1 and 3x minus 1. If you test x equals 1, both expressions equal 2. It looks like they are equivalent, right? But if you test x equals 2, the first expression gives you 3, but the second one gives you 5. Since we found one number that produces a different result, we know they are not equivalent. This is why simplifying with properties is the only true proof. Let's use substitution to check for equivalence. We have expression A, 2 times the quantity k minus 5, and expression B, 2k minus 10. Let's try k equals 4. For A, we get 2 times parentheses 4 minus 5, close parentheses, which is 2 times negative 1, which equals negative 2. For B, we get 2 times 4 minus 10, which is 8 minus 10, which also equals negative 2. Since both equal negative 2, they might be equivalent. In this case, they are, because expression B is just the distributed form of A. Substitution is most effective when it helps us prove that two expressions are not equivalent. Consider expression C, 3 times the quantity y plus 2, and expression D, 3y plus 2. Let's test y equals 5. For C, 3 times parentheses 5 plus 2 close parentheses is 3 times 7, which is 21. For D, 3 times 5 plus 2 is 15 plus 2, which is 17. The results are different. Because our test value of y equals 5 gave us different results, 21 and 17, we can definitively say that expression c, 3 times the quantity y plus 2, and expression d, 3y plus 2, are not equivalent. Remember, if we can find even a single number for the variable that gives different results, the expressions are not equivalent. When using the simplification method, you must be a master at identifying and combining like terms. Like terms are terms that share the exact same variable and the same exponent. For example, 4x and 5x are like terms, but 4x and 4x to the power of 2 are not like terms because the exponents are different. You can only combine the parts of an expression that are truly alike. Let's check for equivalence by combining like terms. Expression e is 7a plus 1 plus 2a. Expression f is 9a plus 1. To simplify e, we use the commutative property to group the 7a and the 2a together. 7a plus 2a combines to 9a. The simplified expression e is 9a plus 1. Since this is identical to expression f, they are equivalent. Be especially careful with expressions involving exponents. As we learned, x to the power of 2 and 2x are almost never equivalent. An exponent means repeated multiplication, which makes the number grow very quickly. If you plug in x equals 5, x to the power of 2 is 25, while 2x is only 10. The difference in value shows clearly that these expressions are not equivalent. Let's check equivalence for expressions with exponents. Expression g is 5 times the quantity k to the power of 2 plus 3. Expression h is 5k to the power of 2 plus 15. To simplify g, we distribute the 5 to both terms inside the parentheses. 5 times k to the power of 2 is 5k to the power of 2. 5 times 3 is 15. The simplified expression is 5k to the power of 2 plus 15. They are identical, proving they are equivalent. The subtraction sign in front of a parentheses can be tricky. Look at expression I, 6 minus parentheses x plus 3. This means you are subtracting the entire quantity x plus 3, which is the same as distributing a negative 1 to the parentheses. So, the x becomes a negative x, and the positive 3 becomes a negative 3. The expression becomes 6 minus x minus 3. Let's use negative distribution to check expression j, 10 minus 2 times the quantity y plus 1, and expression k, 8 minus 2y. To simplify j, we distribute the negative 2. Negative 2 times y is negative 2y. Negative 2 times 1 is negative 2. So j simplifies to 10 minus 2y minus 2. Combining the like terms 10 and negative 2 gives us 8. The final simplified form is 8 minus 2y. This is identical to k, so they are equivalent. The properties of operations work even when the coefficients are fractions. Look at expression L, half times the quantity 4x minus 6, and expression M, 2x minus 3. You need to distribute the half to both terms. Half of 4x is 2x. Half of negative 6 is negative 3. The distributed form of L is 2x minus 3. Since we just found that expression L simplifies to 2x minus 3, and expression M is already 2x minus 3, we can conclude they are equivalent. This confirms that all of our properties, especially the distributive property, apply to coefficients that are fractions or decimals just as they do to whole numbers. Let's summarize the properties method. This method is superior because it provides a complete proof of equivalence. If you can simplify both expressions down to the exact same form, you've proven that they will have the same value for every number possible. It takes more work than substitution, but the conclusion is certain. This relies on your mastery of combining like terms and the distributive property. In conclusion, you had two tools to identify equivalent expressions. Remember that substitution is a good tool for a quick check, and more importantly, it only takes one different result to prove that expressions are not equivalent. But the definitive proof is achieved by simplifying both expressions using the properties of operations. If the simplest forms are identical, you know the expressions are equivalent. Master these methods, and you'll always be able to identify algebraic twins.